Hi guys, it's time for some power stuff again. And of course a power supply. What you see here is quite old design. I have this thing for, I don't know, 3 years or something. Never used it. And to be honest, I wasn't really interested in using it, just bought it just to have it because it looked interesting at that time. Now, I thought, okay, it's time for reverse engineering again. And well, this is why it looks like that. I removed everything that it was on. I don't know why they need a small heatsink on the TL494. Unnecessary. Anyway, bye-bye. Everything removed, completely reverse engineered to see how these things, how good, how bad, what the quirks are, what they did. Anyway, this thing is called, by the way, this is the teaser. That's a part of the reverse engineering. There's a second page of that. This thing is called an SZ-PD07 CCCV, not CCTV or not CCP, no CCP. It's CC, constant current, constant voltage, 1200 watt, 20 amps. This is written, I think, here. Yeah. From my understanding, for what I see from after the reverse engineering, this thing is just one design and they just add or remove parts to make it 1500 watts, supposedly, or 1800 watts, supposedly. As you can see here, there is already one output sense resistor that is not populated because it's, for this model, it's not necessary. Same with the third 20 amps fuse. Yeah, well, this is how it looks. This video will be in no means a review of that thing. I'm not interested in a review. There are thousands, thousands, it's a little bit too much, but hundreds of reviews from this kind of power supply. My video will be a complete walkthrough of the schematics and explanations of some interesting parts and a small test at the end. No review. And we will see a little bit what it does. Oh my God, that blinks much better like that. So let's start with a reverse engineered part. And of course, I missed to show you what I wanted to show you. Look, this is the part. Let's go a little bit closer. This is the MOSFET, the source of the reverse polarity MOSFET. And this is, let me show you, this part here. This trace here is this trace here that goes there to a via. This is the sense wire or the sense trace. Just I wanted to show you that so you have seen it. Let's continue. Okay, now that I've stripped almost everything down, at least the big parts, and the biggest part is this heatsink. Let's try to focus again. Yeah, this heatsink. We can see here 3 blue seal pads. These are for the TO 220 package parts. These two parts are these two are for the output diode, Schottky diodes, and this is for the MOSFET that is used that is used for the reverse polarity protection. Why they use such a cheapy seal pad, a thin seal pad, and a thermal compound only for the main MOSFET, the switching MOSFET. That's a TO247. I don't know, but this is how they did it. This is how it looks. It's not bad, but this is not the reason what I wanted to show you. Since I have everything down, this is the switching inductor. It consists of 2 stacked cores. It's quite powerful. We have here, I took it out to measure it. If I knew what I did to myself, I wouldn't do it, but I'll show you why. We have 14 windings with each 4 AWG16 strands in parallel. That can take a lot of beating, yeah? But to get that out and to bring these 4 strands more or less nicely in parallel again, to get it to these holes, that was a nightmare. Why didn't they do just a little bit bigger round holes on both of sides and Bob's your uncle? Anyway, this is how it looks. On the back, this is the MOSFET for the reverse polarity protection, the switching MOSFET, and the 2 output diodes. I will show you everything in detail when we go through this. Woo! Why we have such a bad? No, it's better. We go through this complete reverse engineered schematic. What I wanted to show you is the part of the input overcurrent protection. This is quite interesting. Yeah, let's say so. This is how it looks. This here is a reverse polarity protection MOSFET, quite a beefy one. I will show you again the data of all the interesting active components that they use here. This shunt here is not a dedicated shunt. It is a part of the PCB. It is the PCB trace or polygon, whatever you want to say, to name it. They use it as a shunt. I tried to measure it, but I measured it from this point here to this point here, where the 2K is, and it comes out 1 point something milliohms. Yeah, I don't know. Anyway, the idea of the whole sensing is that you have an resistor divider with, on the low side, on the bottom side, a variable negative offset. As current passes through this in Mark's resistor, here is a negative voltage in millivolts generated. Millivolts, microvolts, I have to check it. I calculated probably microvolts. Yeah. And this is used as the offset, as the negative offset to this resistor divider. The main point, the midpoint of this resistor divider goes then to the 1/2 of an LM358 that is working as a comparator with a resistor, a capacitor in parallel between negative and output to reduce oscillations. And they put on the positive input a 2K resistor to ground. Honestly, I do not understand how this works. This would work on the overcurrent protection, would activate, and this would light here the LED only if the positive input is more positive than the negative input. But how should that work? Do they rely here on the input bias of the LM358 but it's nanoamps. even if it's 40 nanoamps. Through a 2K resistor, it's not enough to generate millivolts, because here you have millivolts. Yeah, I don't know. Honestly, I don't know how this works. The only idea for me, what I have, is that they're using the bias, the input bias, to generate this offset. But with a 2K, far too low. If it was a 2 mega ohms, yeah, that's something else, but 2K. Anyway, if somebody knows a better explanation how this works here, in combination with this PCB trace resistor and this variable offset, negative offset on the bottom resistor divider, just write it in the comments. I would like to know what you think about that. So, all the rest will be shown when we go through all this thing, yeah, because I divided it in two schematics. This is the main switching schematic, and this is the auxiliary power supply, or the controller power supply, that consists of this controller and this inductor, and the controller for the fan. It's just an on-off controller. If the heatsink reaches a dedicated temperature, it just turns the fan on. If it goes down, it turns it off. That's all. But this is again a dedicated part. So let's put this thing together and go through the schematic. So let's go through now the whole schematic. Honestly, it is not a very big thrills design. It's a boost converter. Let's start from left to right. You have the input, 10 to 60 volts. 3 fuses in parallel. On my board there are only 2 populated, 1 and 2, each 20 amps. We have a reverse polarity protection with a powerful MOSFET. I will show it to you, the data, when I finish with the walkthrough of the schematic. Here we have the very interesting input current protection that uses a PCB shunt that I showed you before when I had it open, or explained it, and where I said I'm not really sure how this thing works. I don't want to repeat it again. Then we have the second half of the LM358 is used as a input undervoltage protection. It is just gives a set point using the 5-volt reference that is generated from the TL494, the VRF here. This is fed to the positive input, and the negative input of the comparator, because now this op-amp is used as a comparator with a capacitor that damps the oscillations. The negative side is in the midpoint of a resistive divider that samples the input voltage. That's for me VU here after the fuses. That means that if this divided down voltage is less than the set point voltage set with the RV1 trimmer, this one, the output of the comparator goes high. It lights up the UVB LED. There's somewhere here. Okay, it's called UVLO, yeah. And goes like that to the positive input of the TL494 and shuts the PWM of the TL494, or it regulates it down. This is an additional feature because we are using this input of the TL494 that is used for setting the voltage to. And you see it is just an or that, 1, 0, 1, 1. If either of these two, if the output overcurrent protection, input overcurrent protection goes high, or the under voltage protection goes high, it shuts down the TL494, or at least it regulates the PWM very low down, so you don't get any output or a very low output anymore. So this is the input protections that we have, as you see here. Let's go a little bit nearer. We have 4 capacitors, bulk capacitors, filter capacitors, reservoir capacitors in the input. These 4 here. By the way, that's the LM358. We go to the massive inductor. That again is a stacked 2-core inductor. It's a little bit crooked put now inside because it wasn't that easy to put it inside again. That was me that it's so crooked, but it works. Yeah, anyway, look. If I knew, as I told before, if I knew what I do to myself when I take it out, I wouldn't have taken it out. Anyway, this is inductor, 40 microhenry from what I measured. We have the switching transistor, the switching MOSFET. It's a as you can see here, NCE Not 1 H21T. It's a powerful, and it has a TO247 casing. It's down there. Then we have the 2 output diodes, one on each side. These are double diodes. Bad thing is that they use MBR 3100 diodes. That means 100 volts. And this goes up to 90 volts, so the headroom is relatively low. But honestly, these are 30 amps each of these packages. There are 2 in parallel. So this is exactly what I mean. This design is made for higher power too, and they just populate it or leave what they think, and the rest is taken out. Okay, anyway, the power MOSFET, the driver transistors that are in a totem pole configuration. You can see it. Let me show you here. These 2. Yeah. Nothing special. Let's go back. Output capacitors, 3 capacitors in parallel. The trimmer for the output. And then you have, again, let's go near here, the output connectors and the sense resistor. That's a 5 milliohm. And what I could measure with my meter that I have, that is not the best one. This is this one. You can see there is a place for a second one for higher power, higher current. Then we go through a low pass filter to clean a little bit the sample that we get here from the current, and go directly to the iSense input of the TL494, that is pin 16. Here we have the damping loop, the compensation capacitors and resistors for each loop. One loop for the voltage is made for R15 and C6, and for current we are using the R23, C13 and C12. The first input, the first op-amp on the TL494 is used for regulating the voltage, and the second one the current. Then we have a set point again here for the voltage to set the maximum voltage, and we are sampling the voltage from the V out, that's the output here, through these variable resistors. Yeah, for this variable resistor divider, and that's it, nothing else. This is the RV2, the output trimmer here. So what else we have? Same thing for the current adjustment. We have here, instead of setting a fixed reference point for a maximum or minimum, we have a variable reference point made from this variable resistive divider, and we are just sampling through this LC filter directly to the positive input of the second op amp. As you can see here, the negative input goes through this variable set point. Yeah, nothing much to say here. CT, RT are the settings for the oscillator frequency. Is there anything still interesting here? Yeah, from what I don't understand is we have here a single output configuration because we are only switching one MOSFET, and we don't have a push-pull or a half bridge that needs two MOSFETs. And the out C, that is the mode pin of the TL494, is striped as it would be, as the output would be a push-pull or a half bridge. That means that the two outputs are out of phase and 180 degrees. They are connected in parallel, so it doesn't really matter, but I don't know why they do it. There is a dedicated mode for that, and normally the out C would be striped to ground, then you have a single output, or to VREF, and then you have a push-pull output, for example. Okay, they did it how it did it. So this is this part. Let's continue to the second part. Here we have the second part of the schematic. I divided the schematic on the primary, the main, control and power loop. And then we have the auxiliary, again out of focus, go here. The auxiliary power supply, that means that's the power supply for the controller and the fan. Interesting thing is that they're using the same power supply that they use for the controller. You see here they're powering the LM358, and from the same power supply they supply the fan too. I wouldn't do that, but okay. This power supply is not intended as a lab power supply. It's just something that, yeah, you can use it for, I don't know for what. For nothing sensitive, at least. Anyway, they use here the XL7005. That's a high voltage input step-down converter. This is this one. This one. Of course, it is all the chips except of the dual op-amp are grounded. Yeah, the labelings removed. Pointless, really pointless, because if you want, you can find it out. Anyway, that's the 100, that's here the 100, whoa, where is it? That's the 100 microhenry inductor for the auxiliary power supply. This one here. Then you have the feedback loop. And that's it, there's nothing more to say. The auxiliary voltage, or the controller voltage, is roughly 13.5 volts. That's it. And you can see it is used as the VCC voltage here for the TL494, and of course for driving the outputs of the TL494, the two BJT outputs that drives again the totem pole, that drives again the big MOSFET. Yes, what else? Yeah, and the last thing, it's a little funny how they did it. It's the fan controller. It's just an on-off controller. They use an SMD NTC thermistor. I measured it 20K at 25 Celsius at the moment. The whole idea is they needed a switch point, so they needed some kind of a reference. The reference is made, I didn't wrote what is what. These two are TL431. See, I knew I forgot something on the schematic again. Anyway, this is a low-cost reference. I will show you later how it works and why they use that. The first one, this part, sets just a 10-volt reference voltage, nothing else. This is fed directly to a voltage divider consisting on the upper part of the NTC and the lower part of the 10K resistor. And when it reaches 2.5 volts or more, it triggers the second TL431 that in its way it goes low, the output goes low, and it opens the PNP transistor, and this one starts the fan. That's it. A cheap way to make a on-off fan to start a dedicated temperature. Otherwise, they would have to use perhaps an op-amp. Then they have to make more components. Anyway, this is a cheap TL431 is very cheap, so they used it. This is the small PCB that I showed you before that is screwed on the heatsink. So these are more or less the complete schematic. So and now a few more informations about the design, and the most important one is that this complete caboodle here is not electronically short circuit protected, output short circuit protected, in no means. You can see it very easy. There is no pass element that would remove the input from the output in case of a short. The only thing that protects the input from the output in the case of a short circuit are these these fuses. And this is our automotive fuses. They are not fast fuses. So the second thing that protects perhaps the whole system from burning up in a case of a short are these two double diodes. And why? Because each of these packages here contains two diodes that can carry 15 amps. That means each package is for 30 amps rated. And you have two then in parallel. That means 60 amps normal operation, peak much higher for a short period of time. And it is very interesting why they left the second one on the converter if only one would be needed. So it makes me think that they let it just to be perhaps to give it a higher possibility that if a short occurs on the output, that these four diodes more or less give more time for the fuses to blow because they are overrated here. We have at least 60 amps normal, and it will go way higher for milliseconds here. So perhaps this is the only reason. But as it is, only the fuses protect the whole system. And the possibility, of course, is high that it depends on the quality of the output diodes that they will survive or not. But it would be quite easy to make an electronic output short circuit protection because they have a pass element. This one, it's on the ground side, and it would be very easy Depending on the output current, let's say, so I don't know, they could dimension it to say 60 amps, 50 amps, 50 amps. Yeah, that's below of the output diodes. 50 amps means that there's a short circuit, and it will trigger with a little, very little circuitry, that the gate of this MOSFET goes to zero, to ground, and not to full auxiliary voltage, 30.5 volts. That means completely open. So that would close this MOSFET, and then everything would be hanky dory. Yeah, they didn't do it. Would be very easy to accomplish this, but just for information, this is how it could be done, just by adding a few more parts and controlling this reverse polarity protection MOSFET. So let's continue now to a few interesting data sheets. This is the first one. That's the switching MOSFET, quite powerful one. All the MOSFETs they use here are for NCE power, at least on my DC-DC converter board. I used NCE power parts, components, products for quite a long time, because I like the Asian, the parts that made for the Asian market here. They are specific for a job, and they do it very well, and they are quite cheap. Of course, not from AliExpress or from eBay, but from the distributors that I trust, like LCSC and a few other ones that I have. Anyway, blah, blah, blah. This thing can go up to 100 volts. That's not the highest value that I would expect, because if the output goes up to 90 volts and with a small tinkering on the schema on the design, you can go over this 90 volts. So the headroom is not very high, but it works. Enough power for everything, enough current for everything, 210 watts. And the most important thing is that it has an RDS on of 4 milliamps, less than 4 milliamps, with a VGS of 10 volts. And we achieve that easily because we are not getting in any means into the linear region. That means that it is either completely on or completely off for a time of T. The T is the duty cycle. Yeah, that's it. And yeah, this is the dissipation power. Let's continue to the next one. This one is the reverse polarity protection MOSFET. Again, powerful, 80 volts, drain source, 160 amps, completely can handle everything here, and will not get warm because it is either completely open or completely closed again. Yeah, that means the maximum RDS on would be less than 4.7 milliohms. So not really a problem with that, a VGS of 10 volts. And we achieve that very easily because we have connected the gate to 13.5 volts, that's the auxiliary voltage, through a 4.7 ohm resistor. TO220 package, the primary switching MOSFET was a TO247 package, a bigger one. Again, big, powerful, and enough to handle everything. Now we have the output diodes, and as I said before, one of those packages, TO220 packages, would be enough because it is rated for 30 amps. It consists of two Schottky diodes that can carry each 15 amps, that means 30 amps. The 30 amps would be enough for at least for my DC-DC converter. I wouldn't need the boost converter that I have, I wouldn't need two of them. But perhaps they left it just in the thought that when we have two of those in parallel with 60 amps operational current and much higher current for a few milliseconds, that will give enough time for the fuses to blow in the case of an output short. But this is just a thought here. because normally the Chinese do not leave parts that are not needed on the board. Yeah, but this would be the only thing that gives the fuses some more time to blow before the diodes themselves blow. So this is how they look. Again, only 100 volts because they are using the MBR 31100. The headroom is quite low, it's only 10 volts. It would be nicer if they have used the 3200 for 200 volts, but okay, this is how it is and it works perfectly. That's the last part. I want to show you a datasheet. Everything else is just standard stuff. TL431 and the TL494. Yeah, that's I show them many times. The only thing that makes this part shine is the higher input voltage. That's all. Otherwise, it is a very standard step down buck converter with a 180 kilohertz fixed frequency and an output of half an amp. Nothing really to write home here. It comes in two packages. The one is the SOIC 8 that looks like this one, and a SOIC 8 PE that has an exposed pad on the bottom for cooling. And if you see my part that I designed here, I use the part with the external cooling pad. So this is all what I wanted to say for means of datasheet. Yeah, the oscillator frequency here is roughly 150 kilohertz. So that's all. Let's continue. Well, now that I showed you the internals, the schematics and everything, first of all, if you like what you see, if you like my videos, give me a thumbs up. Consider subscribing on my channel. Most of my viewers, most part of my viewers are non-subscribers. Guys, it's just, it's free. It doesn't cost anything, it helps me a lot. Please subscribe to my channel, give me a thumbs up, and press the notification button. What you see here is now what my load, my Kunkin load is possible to do, 400 watts. And we have at the moment 89 volts, almost 89 volts, yeah. At 4 amps, that's 350 watts. And the nothing is getting hot, of course, because it's only 4 amps. Here on the DC-DC converter itself, yeah, my thermal finger, you see, this is my infrared thermal finger, and if this one says, if it doesn't say ouch, then everything is okay. It's getting a little warm, but it didn't even start the fan, yeah, because it's hand warm, yeah, a little bit more than hand warm. The inductor itself is absolutely cold. The output capacitors are cold. Input capacitors are cold. The TL494 is hand warm. Yeah, perhaps wasn't that a bad idea to put the small heatsink on it. But anyway, this is maximum what is possible. Yeah, this is what you see. So now I maxed out, honestly, my Kunking power supply in means of current, or power, let's say so. We're at almost 400 watts, 391 watts. It's 17 amps secondary. It is 23 volts. And the input is 20.6 volt at 21 amps. Here you can see it better. And let's see what is getting hot and what not. The whole thing, it's starting to get hot, but the fan didn't start it yet. There's nothing getting hot here. So what about my thermal infrared finger again? Ooh, ouch, 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 this is getting hot. This shunt is getting really, really hot. Yeah, well, this is how it is. 17 amps, 39 watts, I don't have more. To be honest, more than 17 amps, by 20 amps, this will get critical. I don't know if it will make it, or that will desolder the shunt itself. We have here on the back side the trimmer for the, come on, let's go a little bit near. The trimmer for the output voltage. This is the trimmer for the output current, and this is the trimmer for the input low voltage protection. Yeah, UVLO. Yeah. So that's it. Of course, the schematics are available on request. So that's it for today. I hope you liked it. Most important, thank you for watching. Stay safe, my friends, and see you next time. Cheers.